Welcome to Homework Lib.
This is chapter 35, problem number 44. We have two sources, A and B. The distance between the two is D, and the A is a quarter period ahead of V. So if you're looking at, this is the central line that I just drew. If you're looking at above the central line, then the delta x would be this, delta x, and we have the angle theta here. Now what we're looking for is that the at what angles these waves cancel each other out above and below the central line. So let's start by saying sine theta is going to be equal to delta x divided by d. From here, delta x would be equal to d sine theta. Now, delta x prime then equals delta x plus lambda over 4, because the phase difference between the two is by a quarter wavelength. So then that is going to be equal to d sine theta then plus lambda over 4. So we are looking for the destructive interference, right? We want the waves to cancel each other out. So for destructive interference, we have delta x prime then m plus half times lambda. So then let's plug this in for delta x prime, d sine theta plus lambda over 4. Now if we isolate the angle out of here, because we're looking for the angles, right, at which these two waves emitted by these two sources cancel each other out. So then the sine theta is going to be equal to m plus 1/2 lambda minus lambda over 4. Then it's going to be equal to m plus 1/2 minus 1 over 4. So then here we have lambda times m plus 1/2, right? This is going to be equal to d sine theta. Let me go to the next page. So we said d sine theta is going to be equal to lambda times m plus a quarter. Now let's isolate sine theta. Let's divide both sides by d. So sine theta equals lambda over d m plus 1/4. Then let's isolate theta out of this. So inverse of the sine, lambda over d. Let's use a different type of brackets here. This gives us the angle. However, in the problem, we're not given lambda. We're given the frequency as 444 hertz. In order to get to the lambda times frequency is going to give us the speed of the wave, right? In this case, it's a sound wave. Then lambda can be written in terms of the v and the frequency. So we can plug that in here. Sine v over frequency times distance m plus quarter. So this is the equation that is going to give us the angle, right, at which the waves coming from each sources are canceling each other out. From here on, we're going to be just plugging in numbers and calculating for different m values, right? So for m equals 0, then our theta is going to be, again, inverse of sine. V is 340 meters per second divided by 444 hertz times, d is given to us as 3.5 meters, times 0 plus 1/4, right? So if we do the algebra here for m equals 0, the angle that we get is 3.14 degrees. So if we do the same for m equals 1, the only term that is going to change here, this is going to change to 1 from 0, right? But the rest is going to be the same. So I'm just going to write the answer here, but you know what to change in this equation. We are only varying m. So for m equals 1, theta is going to be 15.87 degrees. For m equals 2, theta is going to be equal to 29.5 degrees. For m equals 3, theta is going to be 45.3 degrees. For m equals 4, we're going to have theta equals 86.41 degrees. For m equals 5, though, if we plug this in, we figure out soon enough that this is giving us for sine theta something greater than 1, which cannot be happening. So that's when we should stop. So the answers, we have 1, 2, 3, 4, 5 answers for when we're above the central line, right? So now let's go. So we're not finished yet. So let's go and figure out for the lower side what happens, what angles we have. So then it's pretty much the same idea, right? A and B, this is the central line, and now we're just looking at it from a different angle. So this is going to be our delta x, and this is our d and everything. So it's pretty much the same. This time only delta x prime is going to be delta x minus lambda over 4, right? Still, d sine theta is our delta x. So then d sine theta minus lambda over 4 is our equation. This is going to be equal to m plus 1/2 lambda from the destructive interference. So then we're going to solve this. We're going to isolate the term that has sine theta. So d sine theta from here is going to be equal to m plus 1/2 lambda plus lambda over 4. Now lambda m plus 1/2 plus 1 over 4. This gives us lambda m plus 3/4, right? So this is d sine theta. If we divide both sides by d and then isolate theta, then, oops, excuse me. If we isolate theta, then we have inverse of sine lambda over d m plus 3/4. So instead of lambda, again, we can do the same. We can put d over frequency. So then we're ready to go. Plug in the values for m and then figuring out what the angles are, right? On the next page, let's do that. So for m equals 0, I'm going to write it openly, right? Theta is inverse of sine 340 over, it doesn't change, 3.5. This term doesn't change. We only have 3/4 here. This is going to be equal to 9.44 degrees. So for m equals 1, I'm not going to rewrite it, but we have 1 plus 3/4, this term, when we're calculating. You're going to find to be 22.51 degrees. For m equals 2, you're going to find 36.99 degrees. For m equals 3, you're going to find 55.13. For m equals 4, it's, again, sine theta comes out to be something greater than 1. This cannot happen. So we stop here. So we have 1, 2, 3, 4 solutions for the second part.